In this video, I will go through problem 2015, this very long titration problem. Alright, so we got potassium sorbate. You can read the formula there. Molar mass is given. That's good. Tells you what it's used for. That's inconsequential. It says the student titrates 45 mils of the stock solution. So we'll probably need that later. With a 1.25 molar HCl, we're probably going to need that, using both an indicator and pH. And then they gave us the Ka. Definitely probably going to need that. Alright, so write the net ionic equation. So there's different ways to attack that. I prefer to just write the full equation out, and then I'll go back and do the net ionic. Some people like to just take away spectators first. Alright, so if we do our double replacement there, we get HC6H7O2. That's sorbic acid, and then KCl. And so we can kind of see right there that KCl is a spectator, all of it. So the net ionic equation C6H7O2 plus the hydrogen ion gives me the weak acid. Alright, part B, a total of 29.95, I think you just couldn't make it 30, huh? Of 1.25 molar HCl is required to reach the equivalence point. We're going to calculate the molarity of potassium sorbate in stock solution. Alright, so remember that we have 45 mils of the stock. So I'm going to go to a piece of paper here. I'm going to carry that information with me. And then I'm also going to take my starting materials, 1.25 molar HCl, and we've got 0.02995 liters of it. Let's find the moles of the acid. 1.25. Alright, so we're going to use 0.0374 moles of HCl. Alright, from our chemical equation we can see this is a 1-to-1 ratio using either equation. You don't have to use the net ionic for the stoichiometry, you can use the regular one. And so I need to show my stoichiometry. 1 mole of HCl per 1 mole of, let's just call it potassium sorbate, whatever. Just a technical step. Alright, and then we're going to finish that off. The molarity will be 0.0374 moles over 1045 liters. .832 molar is my initial concentration. Alright, so that's a pretty straightforward titration problem right there. You're just finding the equivalent number of moles or moles needed to get to equivalence and then finding the volume. Classic pre-AP prep stoic polish. Part C. The pH at the equivalence point of the titration is measured to be 2.54. It's low because remember this is a weak base that we're titrating. Which of the following indicators would be the best choice for determining the endpoint? So we had this catastrophe in class, so we'll change around 2.54. So looks like a thymol blue. So yeah, thymol blue is going to be the best answer, and we need to answer that using some good concepts here. So it's the closest to the pH value. I shouldn't use pronouns. The pKa is the closest to the pH value at equivalence. Alright, and then calculate the pH at the equivalence point. Half equivalence point. So this is just another way of throwing that term at you. Half equivalence point is the half titration. We've talked about time and again today. Most important thing to remember is that the pH equals the pKa at the half titration point. So if our, go back up here, the Ka for sorbic acid is 1.7 times 10 to the minus fifth, where you just plug it into the equation here and get pH equals negative log 1.7 times 10 to the minus fifth. Okay, so now some of you may be concerned about this because we've been working with potassium sorbate, which is a base, and then all of a sudden it asks for the pH if they have equivalence. And I'm throwing in pKa's here. So am I violating anything? And the answer is no, because I'm finding pH. If I were looking for the pOH, I'd need the pKb for potassium sorbate. But since I'm asked for the pH, having the pKa using the Ka value of the sorbic acid that they gave me, it's okay. And it's a little confusing, but they're trying to see what you guys would do with that information. So this pH at 2 sig figs, I believe, came out to be 4.77. So that one concerns me a little bit, just with the signs. Alright, and then the initial pH and the equivalence point are plotted on the graph below. Okay, so they're not very big dots, but they're there. Accurately sketch the titration curve on the graph below. Mark the position of the half equivalence point with an X. Okay, so we know from, let me find it up here, the volume. Okay, yeah, so back up to part B real quick. This is a total of 29.95 is required to reach equivalence. Alright, so that's 30. I didn't need that, it's written right there. So at about 15 mils, just to the left of 15 mils, that's where we need to put our X for 4.77. So maybe somewhere like that. Okay. So this is our half point, this is our full point, so we know that we're going to see something like, that was just terrible. My hand slipped. So something like that. We're not going to have a very big turn. I probably turned it a little late. Something like that. This is a pretty weak base. Now the pKb of this base would be like 10 to the minus 11. So if you remember, we talked about the weaker the bases, the weaker the acids, the shorter this vertical section is going to be. Now this is a disaster because my hand slipped, but it would be something like that. What they don't want to see, so this would be bad. They don't want to see this for this acid and base, because this particular situation is nowhere near that steep. It's going to be a very narrow, very short transition time. Alright, well, let's finish off part F here. The pH of the soft drink is 3.37 after the addition of potassium sorbate. Which species sorbic acid or sorbate has a higher concentration in the soft drink. Alright, so we know that if these two are in a half titration situation, meaning they're equal, then the pH would equal pKa, which would equal 4.77. But if the pH is less than the pKa, just use common sense. It's more acidic. It's more acidic, so you know which one you have more of. It's going to be the acid.